Here in this video, I'm going to look at a few more examples by integrating using our substitution. And the example we have here is x times x squared plus 1 to the fourth dx. And we need to determine what are we going to let u equal. Because if we don't use the u substitution, the only way we could integrate this is if we took x squared plus 1 to the fourth and multiply this out, x squared plus 1 times x squared plus 1 times x squared plus 1 times x squared plus 1. If we multiply all of that out and then multiply that by x, then we would have a nice polynomial that we could easily integrate, but that's much more time consuming that we want to do. So that's why we can use this power of the u substitution if we can identify what we want to let u equal. And recall, we typically want to let u equal the inside part of our function. So here's our composite function. To the fourth power is the outside. The inside function is x squared plus 1. So if u is equal to x squared plus 1, then the derivative would simply be equal to 2x dx. And if we look at this example now, we have the dx and we have the x, but what's missing is the 2. Now, because it's only a constant term that we're missing, we can fix that by multiplying in here by 2, but if we do that, that's changing the problem. So to cancel that out, we're going to multiply by 1/2 out front, because remember, we can have a constant pulled out front. So here we have 1/2 multiplied by 2, which is really 1. So if we're multiplying the problem by 1, we're not changing anything. So we're going to have this 1/2 out front, and then we have our integral, and I like to write this as x squared plus 1 to the fourth, and then we have our 2x dx, which all of that is our du. So if we perform our substitution here, we would have 1/2 times the integral of u to the fourth du. Now, in the previous video, we did an example very similar to this, but out front we had the 2x. Because we didn't have the 2x, we had to multiply by this 2 to give us our du, and then we can multiply the 1/2 out front to cancel it out. So therefore, we could rewrite this from x squared plus 1 to the fourth as u to the fourth, and 2x dx becomes our du. So we bring down the 1/2 and we integrate. U to the fourth becomes u to the fifth over 5 plus c, and there's our integration. The only thing we have left to do is for our final step to rewrite this back in the terms of our original variable x. So we would take 1/2 and multiply that by our u value. So it's u to the fifth, so that means we would have x squared plus 1, x squared plus 1 to the fifth power, and that's still over 5. So we could write this as 1/2 in the 5. You could pull it out front and write this as 1/10 x squared plus 1 to the fifth plus c. Or if you prefer, you could actually write it as x squared plus 1 to the fifth all over 10 plus c. So either way you prefer to write it is correct, but just make sure that after you perform the u substitution and you integrate, make sure you put it back in terms of x. So you want to do the final substitution to get your answer back in the original variable x. And once again, we can check this. If you were to take the derivative using the chain rule, we would end up with the original problem. All right, so here we have another example. We have the integral of x squared multiplied by the square root of x cubed plus 2. Once again, we need to identify what are we going to let our u be equal to. And your first guess should be the inside part, which is underneath the square root. So it looks like we're going to let u equal x cubed plus 2. So then if we take the derivative, we get 3x squared dx because the 2 goes to 0. Now, this is the important part. We have to look at the original problem and say, do we have a 3x squared dx in the problem? And we'll say, well, yes, we have the dx and we have the x squared. And once again, we're missing the 3. So in order to take care of that, because the 3 is only a constant, we can multiply by 3 to get our 3x squared, but then out front to cancel it, we need to divide by 3 or simply multiply by 1/3. So that means we would have our 1/3 out front, and then we'd have the integral of, and I'm going to write this as x cubed plus 2 to the 1/2 power. And I always like to group my du, the 3x squared dx. I like to group this du part together over here. And now we can simply integrate, or we can perform our actual substitution. Now, if you practice this enough, you can maybe skip this next step here, and I'll show you what I mean in just a second. If we do the actual substitution here, then x cubed plus 2 is going to become u raised to the 1/2 power, and 3x squared dx becomes du. And we have a very easy integral, so we would simply have 1/3 multiplied by u raised to the 3/2, right? 1/2 plus 1, we would get 3/2. And we could divide by 3/2, or if we're dividing by 3/2, that's multiplying by the reciprocal, so that would be 2/3. And there's your integral. And then your final step is we want to resubstitute back in the variable, so we would have, in this case, 1/3 times 2/3 would be 2/9. And our u up here is x cubed plus 2, and that's raised to the 3/2 power plus our constant. So here we have our answer. Now, I want to show you, after you've practiced enough of these, now again, I don't want you to do this too soon so that you start making mistakes, but if you've practiced this enough, once you get to this point right here, for an example, if you have 1/3 the integral of x cubed plus 2 to the 1/2, whoops, not 1/3, 1/2, and this is why I like to group our 3x squared dx. Now, I like to keep in mind, we know that all of this is going to be our du. So we know eventually, once we integrate, all of that's going to disappear. And we can visualize that really this part is u to the 1/2. So if you can kind of mentally see this already, you don't actually have to do the actual substitution if you're careful, because we could say, well, this is going to be 1/3 out front, and it's going to be multiplied by the integral here, which we know is x cubed plus 2 to the 1/2. Well, that's really u to the 1/2, and because 3x squared dx is all the du, we can kind of ignore that because that's going to disappear. So we have x cubed plus 2 to the 1/2, so that means we would take the x cubed plus 2 and raise that by 1, so 1/2 plus 1 is 3/2, and then we can multiply that by the 2/3. So instead of dividing by 3/2, we multiply by 2/3, and then of course we would have our plus c. So we end up with the exact same answer, because if we multiply, we would get our 2/9 times x cubed plus 2 to the 3/2 plus c. So if you notice here, once you get really good with this, you can save a little bit of work here by leaving out this step. Now again, I don't want you to try to leave that step out too soon. If you actually need to do the substitution here with a u, that's perfectly fine. But after you do a lot of practice, you should be able to mentally think of this step here, and it can save you a little bit of work. All right, one more example here for this section. We have the integral of x cubed divided by 1 plus x to the 4th quantity squared. So what do you think we're going to let our u be equal to? Well, if we try the inside piece, it looks like we would probably pick 1 plus x to the fourth. And I believe you would be correct. If we get 1 plus x to the fourth, if we try to calculate our du, that's the derivative of 1 is 0, so the derivative of x to the fourth would simply be 4x cubed dx. And if we look at the original problem, of course we have the dx, we have the x cubed, but we're missing the 4. Well, again, that's a constant term, so we can certainly multiply by 4, and that gives us the 4x cubed, but if we do that, we have to take care of it by multiplying by 1/4 out front. So now we can integrate. We would have 1/4 the integral, and I'm going to bring this as 1 plus x to the fourth raised to the negative second power, and again the 4x cubed dx. Again, I like to group this du together. And we probably can integrate this, but I'm going to go ahead and do the substitution for your benefit. This would actually be 1 plus x to the fourth raised to the, if we increase -2, that would be what? To the -1 divided by -1. And again, the 4x cubed dx would all cancel out. So you could do it that way, or I'm going to go ahead and do the actual substitution. So we would have u to the -2 du. And you can see that it's going to be a very simple integration again. So it's going to be 1/4 multiplied by u to the -1 divided by -1 plus c. And to simplify this a little bit, I would like to make our u to the -1 a positive exponent. So we would have 1/4 times -1 over u to the first plus c. So if we actually then do the resubstitution, what is our u? Well, u is 1 plus x to the fourth. So we would have 1/4 multiplied by -1 over 1 plus x to the fourth plus c. And we could simplify this a little bit here. We could certainly write this as -1 over, if you prefer, we could take 4 times 1 plus x to the fourth plus c, and that'll look a little bit nicer. And once again, if you want to check this, you can take the derivative of this answer, and you should end up with the original x cubed over 1 plus x to the fourth quantity squared. All right, so there's 3 more examples of using your u substitution. And once again, I just want to emphasize that once you let u equal part of the inside of your function, when you find du, you must have du in the problem or you're not able to integrate. So for these 3 examples, we didn't have du in the problem, but we were only missing a constant term that we could multiply in to take care of that missing piece. Now, if you're missing more than a constant term, if you're missing a variable, an x, then you're going to have to try some other technique, because we cannot, okay, let me stress again, we cannot multiply a x inside and then 1 over x on the outside. It only works if we have a constant term.